Now this is ASFurther Maths Notes, and we're in Unit 2, so we're looking at matrices, and then we're solving simultaneous equations using matrices. So a quick look then at the main principle. We're trying to get the x bit on its own effectively, where these are matrices then. So if we get the x bit on its own, we can't divide by a because it's a matrix, so we need to multiply by the inverse, multiply both sides by the inverse. A to the minus 1 upon a, of course, gives I, so it just gives us ix. We end up then with them. If you take a wee look at this, we can set this up as a, what's that, a 2 by 1. So the first element is x minus 3y, then 5x minus 2y, separating it out about 2 by 2 and a 2 by 1. Goes like that. Then we find the inverse of this matrix and multiply both sides, and it should then give us our answers then as we work through. It's much easier explained by an actual example, so let's take a wee look and see how it goes. So example 1 says solve using matrices. So we split these into two matrices. So our first one is 7x plus 9y. That's our first element. Next element is 5x plus 7y. And that's equal then to 3, 1. I then separate this out. 7, 9, 5, 7 upon xy equals 3, 1. Now why does that work? If you were to sit in, this is a 2 by 2, this is a 2 by 1, so you can't multiply them. If I multiply this by this, I get this. If I multiply this by this, I get this. So let's find the inverse then. So inverse 49, take away 45, so that's 4. So my determinant then is 4, so it's a quarter. Change these two around, that's easy, and change the signs of these ones, minus 9 and minus 5. So I'm now going to multiply both sides of this by the inverse. So it's going to be a quarter upon 7 minus 9 minus 5, 7, multiplied by 7, 9, 5, 7. X, y equals a quarter. 7 minus 9 minus 5, 7, and then 3 and 1. So let's see that everything works out okay. It's going to be a quarter. What do we have here? 49 plus minus 45, that gives me 4. 63 minus 63. Minus 35 plus 35, that's 4. XY, and hopefully you can see that's all going to disappear. That's the unit matrix there multiplying, so we just then have our XY. Quarter in this one. 21 take away 9, I think gives me 12. And then minus 15 plus 7 gives me minus 8. So effectively here then I have X and Y, and a quarter of these then are going to be 3 and minus 2. So that means X equals 3 and Y equals minus 2. Again, if you click on this wee video link at the bottom, you'll get a very, very old video of me doing it, or you could just try it yourself. Example 3 is very, very similar, so that's the one I'm going to run through. So we're leaving example 2 then for the minute, and we can move on then from there. So let's take a wee look at this one. So we want to set this up. So we're going to have 1, 2, 3, 2, 1, 1, 3, 1, minus 2. And that's X, Y, and Z. And that equals then 6, 5, and 1. So we need to find the inverse of this one here. So first of all, we're going to do our determinant. And that's going to equal 1 upon minus 2 minus 1, so it's going to be minus 3. Take away, remember take away, 2 upon minus 4 minus 3, so that's minus 7, plus 3 upon minus, 2 take away 3, that's going to be minus 1. So what does that give me? That gives me minus 3 plus 14 minus 3, and so my determinant then in this case is going to be 8. I go through then my 3 steps to find the inverse here. So first of all is my matrix of minors. a wee bit of work then with this one. We've already done our first row because it should be -3, -7 and -1. Next row, remember I'm cutting out this and this, so it is -4, -3, so that gives me -7. Middle row, middle column, again I'll just do one or two of these so you can see. Middle row, middle column, hopefully you can see that, you can. So that's going to be -2, -9, so that would give me -11. For this one, I cover up my last column on my middle row. 1 times 1 gives me 1, take away 6 gives me -5. Cover up first row, sorry, first column, last row, and we have 2, take away 3, so we have -1. Bottom row, middle column, 1, -6, so -5. And then this one, last row, last column, 1, take away 4, then with -3. So that's our matrix of minors. Matrix of cofactors. Nice straightforward one really. Is going to be changing the signs effectively of this one, this one, this one, this one. So we have -3, 7, -1, 7, -11, 5, -1, 5, and -3. And then our third part is, hopefully you can see okay, we're going to transpose it. I really struggle to spell transpose today. So I changed my first row for my first column. Weirdly it doesn't affect it because it's a symmetric matrix. So -3, 7, -1, 7, -11, and 5, -1, 5, and -3. So the inverse then of this particular matrix, therefore inverse equals an 8th, -3, 7, -1, 7, -11, 5, -1, 5, and -3. And so we need to multiply both sides of this by the inverse. So again, still a wee bit of writing here, but we're okay. So we have an 8th, -3, 7, -1, 7, -11, 5, -1, 5, -3, multiplied by our original matrix. This is 1, 2, 3, 2, 1, 1, 3, 1, -2, x, y, z equals an 8th, inverse again, -3, 7, -1, 7, -11, 5, -1, 5, -3, and we're multiplying that by 6, 5, 1. Multiply this by this, you will of course get an 8th upon 8, 0, 0, 0, 8, 0, 0, 0, 8. I would recommend you check it to make sure I'm right. Divided by 8 then gives me my unit matrix, so I'm just really left with x, y, z on this side. This one here, -18 plus 35 minus 1, so that gives me 16. This row, this column, 42 minus 55 plus 8, so that gives me a -8. And then the last one, -6 plus 25 minus 3, which is 16. So we're very nearly there. That gives us x, y, z equals, and get to that, 2 minus 1, 2. So the solution to a simultaneous equation is x equals 2, y is -1, and z is 2.